In November of 2024, astronomers pointed one of the most powerful telescope arrays on Earth at a single point of light in a neighboring galaxy, a star so large that if you dropped it into the center of our solar system, its surface would swallow every planet out to Jupiter. It was the first time in history anyone had captured a close-up image of a star outside our own galaxy, and when the image finally came back, it wasn't triumphant. It was strange, blurry, and unsettling, because the star wasn't just sitting there being enormous, it was disappearing. Its name is WOH G64, and to understand why this image mattered so much, you first have to understand how confused the entire question of the biggest star in the universe actually is. If you've searched this topic before, you've almost certainly landed on a star called Stephenson 2-18, a supposed red supergiant with a radius over 2,000 times that of our Sun, big enough that if it replaced our Sun, its surface would extend past the orbit of Saturn. That number has been repeated in thousands of videos, articles, and school projects. There's just one problem. Most astronomers now think it's wrong. The distance measurement Stephenson 2-18 size was calculated from turned out to be shaky, and once other researchers ran the numbers with better data, the star's estimated radius fell apart, dropping it out of serious rankings entirely. It's a useful lesson before we go any further. In astronomy, especially when it comes to something as extreme as the biggest star ever found, the flashiest number circulating online is often the least reliable one. The story of how that number got out into the world in the first place is worth knowing too, because it explains exactly why the mistake was so easy to make. Back in 1990, an American astronomer named Charles Bruce Stephenson was combing through infrared survey data of the Milky Way, hunting for massive star clusters hidden behind thick curtains of galactic dust in a crowded, obscured patch of sky toward the constellation Scutum. Ordinary visible light telescopes are nearly useless in a region like that because interstellar dust scatters and absorbs visible wavelengths before they ever reach Earth. Infrared light, with its longer wavelength, slips through that same dust far more easily, which is exactly why Stephenson's survey was able to find something nobody had properly catalogued before, a dense cluster of enormous brilliant stars sitting roughly 19,000 light-years away, later named Stephenson 2 in his honor. For years, the cluster sat quietly in astronomical catalogues, noted but not deeply investigated. It wasn't until later infrared missions and more careful follow-up study of individual stars inside that cluster, that one member in particular, the 18th star catalogued within it, started to stand out as something unusual, unusually bright in the infrared for its apparent distance, which meant it had to be either much closer than the rest of its neighbors or genuinely extraordinarily enormous. Astronomers went with the second explanation. That star became Stephenson 2-18, and for over a decade it held the title of the largest star ever measured, right up until more recent, more careful distance calculations quietly pulled the rug out from under that claim. Stephenson 2-18 wasn't even the first star to briefly wear that crown, and it almost certainly won't be the last, which is really the whole point. Before it, a red supergiant called Scuti spent years being cited as the largest known star, with an estimated radius of around 1,700 times the Sun, only for improved distance data from the European Space Agency's Gaia satellite to shrink that estimate down dramatically to something closer to 700 or 900 solar radii, depending on which follow-up study you trust, roughly half its original size or less. Before Scuti, it was a hypergiant called VY Canis Majoris that briefly held the record, with estimates that have themselves ranged anywhere from under 1,500 to over 3,000 times the Sun's radius, depending on the year and the method used. Look at the actual published history of this title, and it reads less like a settled ranking and more like a rotating cast of candidates, each one confidently crowned the biggest star in the universe, only to be quietly dethroned a few years later once someone got a better handle on the distance. That pattern is exactly why any video, article, or textbook that presents one single star as the definitive permanent answer is almost certainly going to be embarrassingly out of date within a few years, and it's exactly why WOH G64's story is more interesting than a simple crown. It isn't claiming to be a permanent record holder. It's a star we can watch changing in real time using a technique that doesn't depend on the same fragile distance assumptions that toppled every candidate before it. That raises an obvious question, though. If you can't just point a telescope at something 19,000 or 160,000 light years away and read off its width the way you'd measure a table, how do astronomers arrive at a number like 2,000 solar radii or 1,500 in the first place? For the vast majority of the largest stars ever catalogued, including Stephenson 2-18, the answer isn't a direct image at all. It's a chain of indirect physics, and it's worth walking through. because understanding the method is exactly what lets you understand why some of these size claims turned out to be so fragile. It starts with brightness. Point a telescope at a star, and you can measure how much of its light is actually reaching you, a value astronomers call apparent magnitude. On its own, that number tells you almost nothing about the star's true size, because a small nearby star and a genuinely massive, distant one can appear equally bright from Earth. To get anywhere useful, you need a second piece of information, distance. For stars relatively close to us, astronomers can measure distance directly using a technique called parallax, watching how a star's apparent position shifts very slightly against more distant background stars as Earth orbits the Sun, then using that shift to triangulate distance the same way your two eyes triangulate depth. But parallax stops working past a few thousand light years because the shift becomes too small to measure even with our most sensitive space telescopes. For something 19,000 light years away, astronomers instead have to lean on the surrounding star cluster as a whole, comparing its stars to well understood theoretical models to bracket a likely distance, which is exactly why distance estimates for a cluster like Stephenson 2 have historically ranged across a few thousand light years of uncertainty. A margin of error that, it turns out, was large enough to matter enormously. Once you have brightness and a distance estimate, you can calculate luminosity, the star's true total energy output, independent of how far away it happens to be sitting. But luminosity alone still doesn't tell you size, because a small, blisteringly hot star and a huge cooler star can both put out the same total amount of energy. To separate the two, astronomers need one more measurement, temperature, which they get by splitting the star's light into a spectrum and studying which wavelengths of light are present or missing. Different temperatures leave distinctly different fingerprints in that spectrum. Cooler stars, for instance, show the signatures of molecules like titanium oxide and water vapor in their light, delicate molecular bonds that would simply be torn apart in the atmosphere of a hotter star. Find those signatures, and you know you're looking at something relatively cool, which for a star this luminous points towards something enormous, since a cooler surface has to be spread across a much larger area to radiate that same total amount of energy outward. That final connection between luminosity, temperature, and physical size comes from a real, well established piece of physics called the Stefan Boltzmann law. In simple terms, it says the total energy a star radiates depends on two things multiplied together: how hot each patch of its surface is, and how much total surface area it has to radiate from. A star that's unusually cool but still extraordinarily luminous has no choice, mathematically, but to be unusually large, because a smaller, cooler surface simply couldn't produce that much total light. Run Stephenson 2 to 18's numbers through that equation, using its estimated luminosity of around 440,000 times the Sun's output, and a surface temperature of only around 3600 Kelvin, notably cooler than our own Sun's roughly 5700 Kelvin surface, and the math spits out that eye-catching radius, somewhere over 2000 times that of the Sun. The physics of that calculation is genuinely sound. The problem was never the equation. It was the distance measurement sitting underneath it, the one input in the whole chain that couldn't be pinned down with real confidence, and which, once revised, was enough on its own to knock the star's entire size estimate into serious doubt. This is precisely why WOH G64 represents such a different and more trustworthy kind of measurement. So if that famous answer is likely wrong, what's actually the biggest star we've found? The honest answer is that it depends on how you're willing to define found, and that uncertainty is exactly why WOH G64 matters so much. WOH G64 was first noted decades earlier than Stephenson 2 to 18, catalogued in the 1972 by Swedish astronomers Bengt Westerlund, Olander, and Hedin as part of a broader survey of red stars in the Large Magellanic Cloud, a small companion galaxy that orbits our own Milky Way roughly 160000 light years away. At the time, it looked like an unremarkable red giant among thousands of similar catalogue entries, nothing that suggested it was one of the largest objects astronomers would ever measure. It took decades of follow-up observation, much of it led by astronomer Jacco van Loon at Kiel University, who has personally studied this single star since the 1990 seconds, before WOH G64's true scale became clear. For years, as astronomers estimated its radius at somewhere around 1,500 times that of the Sun, using the same indirect brightness and temperature method just described, already enormous enough to place it among the largest stars ever measured with any real confidence. But an indirect estimate is still an estimate, carrying the same kinds of hidden uncertainty that eventually caught up with Stephenson 2 to 18. What makes WOH G64 different and far more reliable is that astronomers eventually stopped relying on that indirect chain of reasoning entirely and found a way to actually see the star's physical disk directly. The tool that finally made it possible is called the Very Large Telescope Interferometer, operated by the European Southern Observatory in Chile. Instead of relying on a single giant mirror, it combines the light collected by several separate telescopes spread across the desert, effectively creating a virtual telescope with a mirror as wide as the distance between them. This technique, called interferometry, is what let astronomers achieve a level of resolution sharp enough, according to the team, to distinguish a person walking on the surface of the moon from Earth. Even with that extraordinary sharpness, resolving a star 160,000 light years away pushed the instrument to its absolute limit. A team led by astrophysicist Keiichi Onnaka had actually attempted this once before, back in 2005 and 2007, using an earlier generation of the same interferometer, but the instrument at the time simply wasn't sensitive enough to pull a clear image out of the data. It took nearly 2 decades and the development of a new, far more sensitive instrument called gravity before the team could finally try again. It's worth addressing an obvious question here, since it comes up constantly in comments on videos like this one. Why not just use a single giant space telescope, like the James Webb Space Telescope, instead of stitching several ground-based telescopes together? The honest answer comes down to a hard limit in optics called diffraction, which says that a telescope's ability to resolve fine detail is directly tied to the physical width of its mirror. Even James Webb's mirror, at about 6.5 meters across, the largest ever launched into space, simply isn't wide enough on its own to resolve the actual physical disk of a star sitting 160,000 light years away, no matter how sensitive its instruments are. Interferometry sidesteps that limit by combining several separate telescopes and mathematically treating them as if they were one enormous mirror stretching across the full distance between them, effectively simulating a telescope far larger than any single mirror humanity could realistically build and launch. It's a technique that trades some things, like the ability to capture a wide, conventional-looking photograph, for an extraordinary gain in one very specific kind of precision, exactly the kind needed to pull the disk of a distant dying star out of what would otherwise be a single featureless point of light. When the new image came back in 2024, it made history immediately, becoming the first ever resolved close-up image of a star outside the Milky Way. But almost as soon as the celebration started, the astronomers noticed something was wrong. The star itself wasn't clearly visible in the image at all. What they saw instead was a bright, egg-shaped cocoon of gas and dust, glowing around a central point where the star should have been sitting in plain view. When they compared the new data against decades of earlier observations of WOH G64, the pattern became unmistakable. The star had been growing dimmer and dimmer for the past 10 years. It wasn't simply hidden behind ordinary background noise, something was actively happening to it, in real time, right as they were watching. The leading explanation is both simple and dramatic. Red supergiants like WOH-G64 are stars in the final act of their lives, enormous, unstable, and prone to violently shedding their own outer layers as they run out of nuclear fuel to burn. As a red supergiant approaches its final chapter, it begins throwing off huge quantities of its own gas and dust into space, material that can eventually cool and thicken into a dense, obscuring shroud wrapped around the dying star. That appears to be exactly what astronomers caught in the act with WOH-G64. The star wasn't shrinking away, it was quite possibly wrapping itself in its own expelled atmosphere, growing harder and harder to see, not because it had gotten physically smaller, but because it was actively burying itself in the wreckage of its own final years. This isn't the first time astronomers have watched a red supergiant do something like this, either, which is exactly what makes the general mechanism credible rather than speculative. In late 2019, early 2020, Betelgeuse, the bright, familiar red supergiant marking the shoulder of the constellation Orion, and one of the closest supergiants to Earth at a mere 700 light-years, suddenly and unexpectedly lost more than two-thirds of its normal brightness, an event so dramatic it was visible to the naked eye, and briefly sparked genuine public speculation that the star was about to explode. It didn't. Follow-up observations from the Hubble Space Telescope and the European Southern Observatory eventually pieced together what actually happened, that Betelgeuse had ejected an enormous bubble of superheated plasma from its surface, material that traveled outward at roughly 200,000 miles an hour before cooling, millions of miles from the star, into a dense cloud of dust that temporarily blocked a large portion of the star's light from our line of sight. By April of 2020, the dust had drifted clear, and Betelgeuse's brightness returned to normal. Because Betelgeuse is so much closer to Earth than WOH G64, astronomers were able to resolve the actual event in real detail and settle on a fairly confident explanation within about a year. WOH G64 appears to be caught in a related kind of episode, a red supergiant shedding material and dimming as a result, but sitting more than 200 times farther away than Betelgeuse, which is exactly why, years on, the WOH G64 story still hasn't reached the same kind of resolution. There's a deeper mystery hiding inside that explanation, though, and it's the part that has actually split researchers into open disagreement. A separate team, led by astronomer Gonzalo Muñoz Sanchez, dug back through more than 30 years of brightness records for WOH G64, hoping to make sense of exactly what kind of transformation they were witnessing. What they found was even stranger than simple dimming. Sometime around 2013 and 2014, the star appeared to undergo an abrupt shift, cooling data suggesting it had transformed from a classic cool red supergiant into something called a yellow hypergiant, a rarer and even more extreme evolutionary stage, one that some massive stars pass through only briefly on their way toward a final supernova explosion. If that reading was correct, it would represent one of the most dramatic transformations ever directly observed in a star of this size, a genuine, real-time glimpse of a dying giant crossing from one violent evolutionary phase into another, but more recent observations have complicated that story even further. Newer data suggests the star may never have fully left the red supergiant phase at all, and that what astronomers were actually watching might be something closer to a temporary extreme pulsation or eruption, rather than a full permanent transformation into a different type of star entirely. The competing explanations sound almost identical on the surface, but actually describe very different fates for WOH G64. One version has the star genuinely crossing an irreversible threshold, evolving into a fundamentally new, short-lived phase on a fast track toward its final collapse. The other version has the star essentially convulsing, throwing an unusually large and temporary tantrum before potentially settling back into ordinary red supergiant behavior, at least for a while longer. Telling those two possibilities apart matters enormously for anyone trying to predict how much time WHG64 actually has left, and right now the published research genuinely can't do it with confidence. As of the most recent published research, the debate remains genuinely unresolved. Nobody currently studying WOHG64 claims to know with certainty exactly what phase this star is in, or exactly what triggered the dramatic changes recorded over the past decade. What everyone studying it does agree on is this: whatever is happening to WOH G64 right now has never been directly observed happening to a star of this size before, and it's happening close enough and clearly enough for astronomers on Earth to actually watch it unfold in something close to real time, rather than piecing it together after the fact from indirect evidence. To really sit with how strange that is, it helps to understand just how enormous WOH G64 actually is, even using the more conservative end of its size estimates. At around 1,500 to 2,000 times the radius of our Sun, this is a star so large that conventional comparisons start to break down. If you placed it at the center of our solar system, its outer surface wouldn't just swallow Mercury, Venus, Earth, and Mars. Depending on which estimate you use, it would extend out past the orbit of Jupiter, engulfing everything in its path along the way. Our own Sun, by comparison, would sit somewhere deep inside that volume as little more than a barely visible speck. Radius alone actually understates just how large a jump this is, because volume scales with the cube of radius, not the radius itself. Take a star 2,000 times wider than the Sun, and you're not looking at something 2,000 times bigger inside. You're looking at something on the order of 2,000 multiplied by itself 3 times over, a factor of roughly 8 billion. You could, in principle, pack somewhere in the neighborhood of 8 billion suns into a volume the size of WOH G64, a number so large it stops feeling like a measurement and starts feeling like an abstraction. And yet, despite that almost incomprehensible size, WOH G64 isn't even close to being one of the most massive stars known. Size and mass are not the same thing in stellar physics, and red supergiants like this one are a strange kind of extreme bloated to unimaginable width, while actually containing only a modest number of times the Sun's mass, packed into an atmosphere so thin and distended it barely holds together at all. That combination, enormous size paired with comparatively fragile structure, is exactly why stars like WOH G64 are considered unstable in the first place, and exactly why they're capable of shedding material as violently and unpredictably as astronomers appear to have caught this one doing. There's actually a theoretical ceiling that makes this instability almost inevitable. As a red supergiant swells, the outward pressure of its own light, radiation pushing outward from the nuclear furnace at its core, starts to rival the inward pull of its gravity. which is comparatively weak given how little mass is spread across such an enormous volume, push that imbalance far enough, and the outer layers of the star stop being reliably held in place at all, prone to being flung outward in exactly the kind of violent mass loss episodes astronomers caught Betelgeuse doing and appear to have caught WOH G64 doing as well. Some stellar physicists have proposed a rough upper limit on how large a red supergiant in our galaxy can grow before this effect makes it fundamentally unstable, somewhere in the neighborhood of 1,500 times the radius of the Sun. It's not a hard wall the way the speed of light is, more a zone where a star's own structure starts actively working against itself, and it's notable that both WOH G64 and the Debunk Stevenson 2 to 18 estimates sit right at, or uncomfortably far beyond, that theoretical edge, which is itself part of why serious researchers treat any claim of a 2,000 plus solar radii star with real caution until it's backed by something more solid than an indirect brightness calculation. There's also a genuinely sobering endpoint sitting at the far side of all of this. Every sign researchers have gathered about WOH-G64, its extreme size, its violent mass loss, its rapid and erratic recent changes, points toward the same eventual outcome. This is a star in the final stretch of its life, and stars at this stage don't fade away quietly. They end in a supernova, one of the most powerful explosions the universe produces, briefly outshining the combined light of every other star in its host galaxy. Nobody can say with any precision exactly when that will happen. It could be within the next few thousand years, which sounds distant on a human timescale, but is an almost immediate eye blink by the standards of stellar evolution. It's entirely possible that the strange dimming and transformation astronomers have been documenting over the past decade isn't a separate event at all, but the opening act of exactly that ending, the first visible tremors of a star beginning to unravel before its final collapse. The frustrating part is that the very same process that makes WOHG64 so scientifically valuable right now may also be what takes it away from us. Researchers involved in the 2024 imaging project have already noted that continuing to observe the star at this level of detail is becoming genuinely difficult, precisely because the same dust it's shedding keeps thickening the veil between it and any telescope on Earth. The teams studying it are pinning real hope on upgraded instruments to keep the observations going, including a more sensitive successor to the gravity instrument, known as Gravity Plus, and the extremely large telescope currently under construction in Chile, which will eventually carry a primary mirror 39 meters across, making it the largest optical telescope ever built once it's operational. Instruments at that scale could, in principle, resolve WOH-G64 with even greater clarity than the 2024 image managed, assuming the star hasn't dimmed itself into obscurity by the time they come online. It's a strange kind of race, better instruments arriving just as their target becomes progressively harder to see. Whether or not we get to watch every stage of it unfold, the explosion in itself won't just be a spectacle. Stars of this size are, in a very literal sense, factories. Deep in their final years, as they burn through progressively heavier elements in their core, and violently in the moment of the supernova itself, red supergiants forge many of the heavier elements scattered throughout the universe, and when the star detonates, all of that enriched material gets hurled outward into space, eventually becoming the raw ingredients for new stars, new planets, and occasionally, over billions of years, new life. Every atom of oxygen you breathe today, every atom of iron in your blood, was forged inside a star not unlike WOH-G64 at some point in the roughly 13.8 billion years since the universe began. That's not a poetic exaggeration, it's the accepted mainstream explanation for where most of the periodic table actually comes from. In that sense, watching WOH-G64 unravel isn't just watching a distant curiosity die, it's watching one link in the same chain of stellar deaths that billions of years ago scattered the material that eventually became you. And that's what makes this story so different from a simple ranking of the biggest objects in the universe. WOH-G64 isn't a static record holder sitting quietly at the top of a list, the way Stevenson 2 to 18 was so often and so wrongly presented as being. It's a live, ongoing event, a star large enough to be measured from 160,000 light years away, currently undergoing changes so dramatic that the scientists who have spent decades studying it are still actively arguing, in papers published within the current year, about exactly what they're looking at. Every new observation adds more data, and so far more data has meant more disagreement, not less. The image that made history in 2024 might not even be the most revealing one we get. Astronomers have already noted that future images may become even harder to capture, precisely because the star keeps growing fainter behind its own expanding shroud of dust. meaning the window to directly observe whatever is happening to WOH G64 of may be closing even as researchers race to understand it, somewhere in a neighboring galaxy, invisible to the naked eye and barely visible even to our most advanced instruments. One of the largest objects we have ever measured is quietly coming apart, and we are lucky enough, purely by chance of timing, to be watching it happen. The question the internet likes to ask, what's the biggest star in the universe, turns out to have a strangely unstable answer, one that keeps shifting as measurements improve and old assumptions get quietly overturned. But maybe the better question, the one WHG64 is actually answering for us in real time, isn't how big a star can get. It's what a star that big looks like in its final years, right before it stops existing in any form we'd currently recognize at all. If stories like this pull you in, subscribe to the channel, because this is exactly the kind of territory we spend our time exploring here. Drop a comment and tell me which part surprised you most. The fact that the internet's favorite answer for the biggest star is likely wrong, the idea that astronomers are still disagreeing over what they're watching happen to WOH G64, or just how close this star may be to its final supernova. Let me know where in the world you're watching this from, and if you want to keep exploring, there's another documentary waiting for you right here on the channel, so stay a little longer, and let's keep looking up.